Okay, so we begin this lecture, for we bring a new topic now, and this new topic will be using all the material that we covered earlier based on that, but this is the key topic in adaptive signal processing, which is optimal filter, also called Wiener, Norbert Wiener, the famous man, and this is FIR filter. Essentially, because IIR filter has this additional requirement of maintaining stability and causality, that the poles must be within unit circle. But so far, whatever research has gone into it, and lots have gone into it over 50 years, I mean, there is no guarantee, nobody could give a guarantee that the filter that they will derive will have, no stability issues and all that. Okay. And even if optimal IIR filters are there, going to adaptive IIR filter from there is impossible, because when it is adaptive IIR filter, there is no guarantee that we will be able to ensure its stability and causality. More about that later. Let us consider FIR filter first. Here, basic structure is this: there is a random process which is maybe 0 mean WSS. Probability density, joint density, all those things can be of any type, that we are not doing here. And you want to pass it through a filter, FIR filter of coefficients W0, W1 dot 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 W capital N minus 1, and filter output is nothing but a linear combination of x n and then x n minus 1, there is W 0 x n, W 1 x n minus 1 plus dot 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 W n minus 1 x n minus this. All right, it is a linear combination of current input and n minus 1, capital N minus 1 past input. They are linear combination multiplied by coefficients and added. These coefficients are so called filter coefficients. They are filtered because they work on current data and n minus 1 previous data, and continuously for every n. That is why it is a filter. But this purpose of this filter is one thing, that is there may be some target response d n, which is a desired response, sometimes called target signal, training signal, and all those. Purpose is to see that you design the coefficient such that y n is a very good estimate of d n. All right, y n is possibly the best estimate of d n. So, that means, if I take the error between the two, plus here minus here, call it E n, E n should have minimum strength. All right. Now, certain notations, this y n you can write as y n, you can write as some w vector transpose x n vector, where w vector is w 0, w 1. So, these coefficients put in a vector form, x n, see the underline, it means a vector, it is a current data vector, sometimes called regression vector, this x n you understand W transpose x n will be what? This is a row column vector. So, after transpose it will become a row vector and then multiplying. So, W 0 x n, W 1 x n minus n dot dot, which is what this. Now, one thing you can say that why not design the coefficient so that d n equal to y n. That you can do. If you equate d n to this right hand side, and there are unknowns W 0, W 1, W capital N minus 1. So, capital N number of unknowns, data is known x n, x n minus 1, this data is known. So, this is just one equation, right hand side is d n which is known, and left hand side is this linear combination where x n known, x n minus 1 known, and all that, W 0, W 1 dot 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 W capital N minus 1, they are unknown. So, one equation, so many unknown. So, you have infinite solution, you can pick up any solution, put that here. So, then y n will be equal to d n, and you are very happy n is 0. But relax, that will not work, because once you design the coefficients and if you put here, Next time at n plus 1th clock, it will be W0 x n plus 1, W1 x n and dot dot dot. That linear combination, there is no guarantee it will be satisfying D n plus 1. In fact, that time error margin could be very huge. Okay. So, that is why this is not a procedure. So, procedure is to design the coefficient so that in an expected sense, average sense, E n has minimum strength. Again, you cannot minimize expected value of E n. Okay. Remember, E n is D n minus Y n, D n is a random sequence. Okay. This is also WSS, 0 mean. Okay. E n is random because D n minus Y n, D n is random, Y n is obtained from the input samples, and input samples are random, x n is a random variable, x n minus 1 is a random variable, so on and so forth. So, Y n is a random variable, D n is a random variable, so difference is a random variable. But you cannot just minimize this, because that does not mean that error will, even if you minimize it, it does not mean error will be less, because E n is 0 mean, so sometimes it will go positive, sometimes negative. So, average could still be very minimal, 0 maybe. So, expected value of this could be minimum possible, maybe 0, but that does not mean that this is not varying over a wide range, which is basically which does not serve any purpose. I want its power, rather I should have this E square n, E n is real here, we are dealing with real case, 0 mean WS is real, this is also real. So, that is why E n is real. So, we just take square of it, there is no complex. So, E square n is the power, average power, and then expected value of that is the average power, which is the variance here. And that is fine, because whether E n goes positive or negative, E square n is always positive, and expected value that will give you the power. This power, if it is less, that means power of E n is less, means its variance is less, that is around mean, it will vary over a smaller range. The increments around the mean, which is 0, will not be having large spread, because then power will be, average power will go up. If it is spread, if it is variation around the mean is small, then in an expected sense, this also will be less, average power. So, therefore, we will minimize this. Now, certain things are given to us here. One is x n d n, they are jointly stationary. X n minus m and d n jointly stationary. Maybe I rewrite it. X m, let me put it m, d n, they are jointly stationary for all m n, meaning, and they are real, meaning if you take the correlation between x and d, r x d k, that is E, you can take any index here, n, d, n minus k, no star here because all are real, gap is k. So, it should depend only on k. Even if one sample is x, another is d, the correlation between them depends only on the gap. So, it is called cross correlation, because one is the random process x, another is d, both are not x. So, not auto correlation, but cross. But even in the cross correlation, that depends only on the gap k, then only you say they are jointly stationary, and that is what is given to us, number 1. Okay. In fact, what is given to us is this vector p, where p is E of this data vector this is the data vector times d n. So, x n d n will be r x d 0, x n minus 1 d n, n minus 1 d n. So, gap is n minus 1 minus n, gap is minus 1. So, it will be r x d minus 1, so on and so forth. So, it is basically r x d 0, r x d minus 1, dot 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 R x d. Last one is n, this index minus this index, so small n cancels out. So, minus capital N plus 1. So, this is given because we must be given some information. So, exact x and exact d n we are not given, neither are we bothered about them, because just one observation of this sequence or that sequence does not matter, because they will change in the next time. But statistical properties is given, that is the cross correlation values between this d n and x n, at least for this many, for 0 lag, for -1 lag or gap, minus capital N plus 1 gap, at least that is given to us. Okay, that is one information given to us. Another thing that is given to us is R x x. And we have studied this earlier, x n, x transpose n, just transpose, not Hermitian transpose, because conjugation has no meaning here, because we are, for simplicity, we are considering real case. Later we will consider extended to complex case, of course. Okay, but right now all are real, x n, d n, and therefore the filter coefficients are real. This x n, x transpose n you have already seen earlier. It takes a triplet structure and it is a Hermitian matrix. It was like this, R x x 0, and this continues, R x x 1, this continues, and this symmetric matrix now, not conjugate, symmetric. So, R x x 1 again will come here, continues, and dot dot dot. It is like this. So, this is also given. The autocorrelation matrix of order, if the length is capital N, so it is basically n cross n. This is given. Okay. So, this information, autocorrelation matrix is given for input process x n, at least up to the size capital N cross capital N, and cross correlation values, at least this many, these values, okay, that is given. We have to now design the filters, so that the variance of the error is minimized. That is, what you have to do is E of E square n, and let me give it in an epsilon square. I could put a function, index n, because after all it is a function of n here, but very soon we will see that because of stationarity, this entire function will be free of the index n, and that is why I am not writing any n here in advance, because I know what it will be. So, no n here, but to start with you could put an n, or if you want I can put an n here, later I will erase it. And this is the variance, this is basically what is, so square of what is E n? E n means desired response minus the filter output, and filter output is y n was W transpose x n. This is your E n, and you have to take square of it, and then the expected value. So, it depends on this filter coefficients present in this vector, it is a filter coefficient vector. So, W 0 it is a function of filter weight W 0, W 1 dot 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 W capital N minus 1. So, capital N number of variables, it is a function of. So, I have to minimize it, so I have to take partial derivative with respect to W 0 equal to 0, with respect to W 1 equal to 0, so on and so forth, and by that process I have to find out W 0, W 1 dot dot dot. Okay, that is called the optimal filter, for which this will be, the variance will be minimum. Okay, let us see one thing. If I expand it, now certain tricks I will apply. This is a scalar, any scalar and its transpose, they are same, because scalar is nothing but a 1 cross 1 matrix. So, I can, if I take a transpose of it, I get back the same thing, because 1 cross 1 matrix transposition is the same. So, I can write it as E n first, that is d n minus into again E n, but that E n I will write as transpose of E n, transpose of E n, E n transpose. E n transpose is E n itself. So, E n into E n square. Now, you break it, E of d n and d n transpose. D n transpose is d n. So, E of d square n, which will be the dn is 0 mean. So, this is the variance of dn and dn is WSS. So, variance does not depend on n. So, variance of dn minus E of W transpose x n dn. Okay. Then other two terms minus, if it is dn, if it is W transpose x n, then dn transpose. Next is dn transpose W transpose x n. Next, if it is W transpose x n dn transpose, next is dn W transpose x n transpose. Okay. It is like separately, if you call it A, in general, if you have something like a vector A, it is a scalar here, but in general a vector A plus a vector B, suppose. Again W transpose x n is a scalar, but I am doing a more general thing. Suppose A plus B, or maybe this I will do later, forget it. You can see one thing, W transpose x n dn, all right. I will write the other term later. Now, here what does it mean? X n into dn. X n consists of all the random variables and dn also random variables. So, product is a random variable and W transpose times that. That means, if you call it a vector, maybe random vector H n, so you have got the elements of H n, because after all x n is a column vector, dn is a scalar. So, dn times every element of x n, and that you get H n, and H n is random because dn is random and all the elements of x n are random. So, H n. Now, W transpose row vector times H n column vector. What we will have? W 0 times the first guy here, W 1 times second guy here, and dot 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 added, then expected. But the expectation then can be pushed inside that summation. We have seen the expectation is linear. So, expectation of a summation of variable random variables means it is a summation of expected value of the value of each of the random variable, and each random variable will be some term from here and some term from here, but this is constant, not random. So, E will come directly on the term from here. So, it will be W 0 E of first component of H n plus W 1 E of second component of H n and dot dot dot, which means it will be W transpose then E of H n. Then you have got the first component, that is W 0 times the first component of E of H n, W 1 and like that, and H n is x n d n, which is given to be cross correlation vector P. In the previous page you have seen. Similar manner, the other term is d n W transpose n x n transpose. Okay. Now, these two terms are same, because this is a row x n d n, if you call it H n. So, W transpose H n, okay, and here it is d n, this is nothing but d n x transpose n W, all right. So, this is, if H n is x n d n, what is H transpose n? This is H transpose n, all right, because H transpose n means d n is a scalar, it is like a 1 by 1 matrix. So, d n will come in the front, d n transpose x n transpose, but d n transpose is d n because it is a scalar after all, and x n transpose. So, this is H n transpose. Okay. So, W transpose H n, row vector and column vector, or H n transpose W, they are same. If I give you two vectors A and B, you can verify they are column vectors. So, if you make it A transpose as a row vector times B column vector, so A1 B1 plus A2 B2 plus A3 B3 like that dot dot, you will get the same thing if you have B transpose A, B1 A1, B2 A2, B3 A3 same. So, these two terms will be same because W transpose Hn or Hn transpose W, this is scalar. So, both are same. Okay. So, again it will be same as what I have here, W transpose P. So, this entire thing will be same, W transpose P, W transpose P. And last one, W transpose X n E of you take the transpose on it. So, X transpose n W transpose transpose, that is W. Okay. Again X n, if you take X n transpose, X n is a column vector, this is a row vector. So, you got a matrix. A matrix, every element is a product of one data of X n, another data of X n. So, it is random. So, random matrix, if you call it A n times W will be again a scalar. So, the entire thing could be maybe H 1 n. So, n times W is H 1 n, which is column vector. So, W transpose W is not random. So, W transpose row vector times H 1 n expected value, as you have seen earlier, it will be W transpose will go out. So, it will be this will be W transpose E of H 1 n, and now H 1 n is A n W, and now A n W you see this is a square matrix. So, every term multiplying the terms here and getting added, that is how you do A n W. On that, if you apply E will not work on the elements of W because they are not random, E will work on the elements here. So, we will get the same thing if you apply E on the elements of this A n matrix first and then multiply that by W, because E does not apply on W, W is not random. So, it will be W transpose E of A n, and A n is this is your A n. By mistake I have erased that page, but does not matter, I can go to another page. So, it will be W transpose E A n W, and A n is X n X transpose n, and E of that is R autocorrelation matrix W transpose R X X. I am dropping that X X from here just for simplicity W. So, expected value of E square n is sigma d square minus the next two terms were same, W transpose P, and this W transpose R W. Now, you see first right hand side is independent of n, and that is why I can write it simply as epsilon square, no need to put a subscript n, and this n has disappeared from here because of stationarity, like E of x n X transpose n is R, that is independent of n because of stationarity, or E of x n into d n, that is P, independent of n because of joint stationarity between x n and d n. All right, that is one thing. Another thing is, you see this is a quadratic function. Why quadratic? First consider this. This will give you W transpose P. So, it is like W 0, P 0, W 1, P1 dot 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 okay, this. But this is first order, not W0 square, not W1 square, this is first order term. But here RW means you have got R, you have got a row of R, W. So, this times W0, this times W1, all that. So, already RW means every term consists of elements of W0 to Wn. And then you are multiplying one, first term here by W0, second term here by W1 and all that. Okay. This first row times this will be the first guy. This is a vector after all, column vector. First guy will be first row times this. That will contain all these elements of W. That will be multiplied by the first element here, W0. So, it will be W0 square, W0 W1, W0 W2, W0 W3 dot dot dot. Then second row times this will give the second guy of this vector. Again that will have W0 to Wn minus 1. That will be multiplied by W1 from here. So, we will have W1 W0, W1 square, W1 W2 dot dot dot. So, that way this is the second order component and this is the first order component. So, overall is a second order function, and therefore, we should minimize this by taking these partial derivatives I equal to 0, 1 dot 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 n minus 1. So, every partial derivative, by the way, epsilon square together is the notation, it is not epsilon and then square. Remember, epsilon square all together is the notation. So, deriving that with respect to Wi. So, you will get capital N equations, one from each derivative at second order. So, if you do derivation with respect to W, W0 or W1 or W2, you will get first order equation. Second order when derived will give you first order. So, you will have a set of first order equations, capital N numbers, capital N unknowns. You solve them and we will get the optimal one, which will minimize this. Okay. But instead of doing like this by individual terms, we define a derivative operator on any function f, a function of the weights. It is nothing but you take the partial derivatives f, like f is E epsilon square here, in general del f del W0, del f del W1 dot 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 dot, I am stacking only del f del Wn minus 1. This is the definition. Then I do this, apply this del operator, derivative operator on epsilon square equate to a vector of zeros, that is, so that will take care of this equation for all the I, because this will be a vector del epsilon square del W0 equal to 0, then del epsilon square del W1 equal to 0, and so on and so forth. So, this is the equation we will be solving, and that I will do in the next class. Thank you very much.